Okay. Hello, everyone. Thanks for attending our presentation, final presentation today. Today, I'm talking about adsorption of a lysine molecule on AU111 surface using a lysine carboxylate ion. Before going to the talk, I will just give a little introduction about the gold substrate. So the unique optical and physicochemical properties of gold make it a strong candidate for using as a substrate in the biomolecular research, sorry. And gold has excellent absorption mechanics, where gold substrates can be used to immobilize biomolecules effectively. So in this study, we utilize the vast simulation packages to measure and justify a strong binding that we obtained by doing the calculations between the lysine and the gold substrate in a certain orientation. So the outline would be talking first about the lysine molecule adsorbed to the surface, which is our model that we use. Then calculations of density of states and partial charge density at two temperatures, 300 Kelvin and 600 Kelvin. Then we calculated binding energy. After that, we have some molecular dynamic simulation for the system after heating to justify our binding energy results. So here I'll start by, in this example, as important studies were conducted on the biomolecules which can be absorbed to the gold substrates. For example, here the gold substrates was modified with carboxyl terminated monolayers to achieve high affinity for specific peptides. So the findings here revealed, for example, better immobilization, coverage, and bioactivity on the gold compared to silicon substrate, which is common used in the biomolecular research. So these findings are crucial for biosensors efficiency, for example, for this model. Gold substrates are also remarkably useful for biomolecules visualizing, and also, as we said, biosensing and binding spectroscopy research. So thus we investigated the binding between a lysine molecule and the gold substrate. So the L-lysine here, why we choose L-lysine, this is our model, why we choose L-lysine, because it has a carboxylate functional group, which is supposed to increase the binding affinity. We hypothesize that it increases the binding affinity of the biomolecules on the absorbed to the substrates, and it has also two amino acids, which are considered the main components of the peptides and proteins. So this is our model. As you can see here, it's composed of 4 layers of gold and just one molecule of lysine, which is positively charged on one of its amino groups and negatively charged on the carboxylated group. So here we started by plotting the density of the states before and after heating the system. The band gap of our system is very, very low. It's overlapping with the conduction band. So comparing to the partial, as we can see here. In the next slide, this is the binding energy calculation. So for the combined system of gold and lysine, we get this E1 around minus 314 electron volts. For gold and lysine separately, we got these numbers, and then we calculated the binding energy by subtracting E2, E3 from E1 to get around minus 20 electron volts, which is very high. So this is why we try to figure out why we get that high energy, binding energy. Because of that, to justify the strong binding energy between the lysine molecule and the gold surface. The heated system here, we could show like from 1 to 8 snapshots for the molecular dynamic simulation. So the heated system has shown that we can see obviously protonation for the carboxylate ion, COO minus, and the protonization for the ammonia, NH3 plus. So here comparing the atomic structure, we can before that. So if we compare the atomic structure, it's obviously observed that the temperature, as the temperature increases, the hydrogen ion breaks from the ammonia and binds to the carboxylate group. So here are the videos that for our model first, so we can show that how it's distributed over the molecule, the atoms in our model. And also the next video is after heating the system. You can see how the hydrogen atoms, like the hydrogen moved from the ammonia to carboxylate group, and because of that, we can say like here we get different situation after heating, while we got another, like the molecule converted from L-lysine, that the one we used before, to lysine molecule with this stable structure. So what we conclude after that, so we concluded like because of the strong binding was verified by heating the system here, and molecular dynamics demonstrated the changes that occurred on the molecule through the heating process. So here comparing before and after adding the energy by heating, the L-lysine was polarized before due to the existence of the carboxylate ion and the ammonia. It was stable, which leads to strong binding with the gold surface. This is what concluded about our situation. But after heating, we noticed that the protonation of the carboxylate ion give us the lysine molecule, which is not polarized, maybe just reduced the binding and also verified the strong binding that we got. So we concluded in summary that depolarization of a lysine molecule because of the heating confirms our hypothesis of a strong binding between our molecule L-lysine with the gold, and that suggested orientation that we applied. This is all about my project, and thanks. Welcome to questions.
Okay, please join me in thanking Lina.